Hey everyone, welcome back to another video by Cam Room 5. In the previous video we have been talking about electrophilic addition of alkenes, and we looked over the very common reactions of alkenes, which include addition of hydrogen bromide or hydrogen halide, which could be hydrogen chloride or hydrogen iodide. Hydrogen remains the same, the halide things vary. Then we talked about the addition of hydrogen, also called as the hydrogenation, in the presence of nickel. Then we talked about hydration, which is the addition of steam in the presence of phosphoric 5 acid. And then we talked about the addition of halogen, which just means decolorization of the halogen, which is normally done for bromine, by the way. In today's video, we're going to be talking about a very new kind of reaction, which is known as the oxidation of alkenes. So we will be talking about the oxidation of alkenes. Now when we talk about oxidation, we should know what oxidation means. The first definition for oxidation is loss of electrons. We know that from our O-level syllabus. The second definition is gain of atomic oxygen. So you react with oxygen, you attach or make a bond with oxygen. And the third definition is loss of atomic hydrogen. So whether you gain oxygen or lose hydrogen, gain of atomic oxygen or loss of atomic hydrogen. There are two kinds of oxidation of alkenes. The first category is with cold and dilute acidified manganate 7. I'll write the whole name of it. It is known as acidified because acidic medium is the one where it reacts. So acidified manganate 7. Why 7? Because 7 is the oxidation number, 7 is the oxidation state of manganese atom here. So this is our main concern here, that the manganate in the acidic medium will react. The another scenario we could have is with hot and concentrated acidified manganate. So manganate is the same thing, but the conditions determine what kind of reactions will happen here. We will have an example here because the cold dilute thingy is really easy. Let's go back to our similar alkene that we have been talking about, which was the asymmetrical alkene. It had two carbons with a carbon-carbon double bond. It was asymmetrical in a way that the red carbon, which is carbon number 2, has two methyls, and the yellow carbon, carbon number 1, has two hydrogens. When we number it, it becomes carbon 1, carbon 2, and carbon 3, while this becomes a methyl. We know it's a 2-methyl prop-1ene. When you talk about the reaction with cold, I should write it a little bigger, cold dilute acidified manganate, the proton means basically acidic medium. So when the reaction happens with cold dilute acidified manganate, you just break the pi bond and you add two hydroxyl groups on both carbons. I'll repeat. You just break the pi bond, everything remains the same. You just add two hydroxyl groups on the double bonded carbon atoms. The red carbon receives one hydroxyl group, the yellow carbon receives another hydroxyl group. We call such a compound as a diol. We call it diol because it has two alcoholic hydroxyl groups. What will be the name of it? Let's number it. Carbon 1, 2, 3. There are two hydroxyl groups, one on carbon 1 and the another on carbon 2. So we started by saying it's a 2-methyl propane, because it's total 3 carbons apart from the branch, 2-methyl propane, 1 and 2 diol, 1,2 diol. We're calling it diol because there are 2 hydroxyl groups. So overall, in cold dilute acidified manganate, just the pi bond goes away, everything else remains the same, you add 2 hydroxyl groups. However, in the hot concentrated manganate, things become trickier. In hot concentrated acidified manganate, things become trickier. You actually split both carbons, you break the sigma, you break the pi. So both carbons will move away from each other. Carbon number 2 and carbon number 1 will break both their bonds. They both move away from each other. I'll focus on only carbon number 2 right now, the one with the red. You can see that it had 2 methyls. The methyls are still here. But the red carbon, which was carbon number 2, now it receives oxygen atom, so it makes a bond with oxygen atom. The carbon number 1 goes away, the carbon number 2 moves away, the carbon number 2 breaks the bond and makes a bond with oxygen. The alkyl groups remain the same. What happens to carbon number 1? The carbon number 1, the yellow one, since it had 2 hydrogens and it was on the terminal, it makes carbon dioxide. So both molecules move away from each other. You have product number 1, which is organic in nature, and then you have product number 2, which is the inorganic gas. So you get carbon dioxide gas, and then the other product is, by the way, a ketone. We'll name it, we'll talk about the naming really quick. Let's have another example. Imagine this kind of compound which has this kind of structure. Let's name it. You start the numbering from the left because the double bond seems to be towards the left. 1, 2, 3, 4, 5. This is your longest chain. There's no branch coming out, so you will name it in a way that pent 2 ene. There's a double bond between carbon number 2 and carbon number 3. There's a double carbon-carbon bond between carbon number 2 and carbon number 3. Let's talk about the reaction with cold dilute and hot concentrated. So with cold dilute acidified manganate and with hot concentrated acidified manganate. With cold dilute, we know we only break the pi bond, so everything literally remains the same. The carbon number 2 has the H and the methyl. The carbon number 3 has CH2 on top and CH3 as the whole chain, while it has 1 hydrogen. Let's number it again. Carbon number 1, 2, 3, 4, 5. Carbon number 2 was the red one, carbon 3 was the yellow one. You attach hydroxyl groups on both carbons which had the double bond. Now it is again a diol. It's a pentanol, so the name will become pentan. The name becomes pentan. 2,3 diol. That is the name. Let's move the name over here it is pentan 2,3-diol. With hot concentrated acidified manganate 7, you break the carbon-carbon bonds, both carbons move away. The red carbon and the yellow carbon, they move away. The red carbon had a methyl, so the alkyl groups remain the same, remember that. The yellow carbon also had an alkyl group, which was a 2-carbon chain, CH2, CH3 remains the same. The bond breaks down, so they both had oxygen attached to them. They both make a double bond with the oxygen. By the way, exactly in the spot where they had a carbon-carbon double bond, now they get oxygen. What about the hydrogens? Because carbon 2 had a hydrogen, remember? Carbon 2 had a hydrogen coming out from the bottom, same as carbon 3. Single hydrogens like these, the one on carbon 2 and the one on carbon 3, hydrogens convert themselves into OH. So the hydrogen will be converted into OH. So technically this becomes a carboxylic acid. I'm highlighting in blue pen. This functional group is known as a carboxylic acid. So now you get carboxylic acids. These are the two products. I'm making a dotted line to show that there are two products. Let's name them. When you focus on the first structure, you can see that this is carbon number 1. I called it 2 to just help you understand that how the reactant was changing, but actually it is carbon number 1 with the OH, and this is carbon number 2. So technically it's a 2-carbon carboxylic acid. The name will be ethanoic acid. Ethanoic acid. What about the structure which was made from carbon 3? It is carbon 1, then we have carbon 2, and then we have carbon 3. So it's a 3-carbon carboxylic acid. We will call it propanoic acid. Propanoic acid. So far we have studied two things. The first thing is that if the carbon-carbon double bond is on the terminal with two H's, it becomes carbon dioxide gas. The second thing we have learned is, if something has methyl groups or alkyl groups, we never change them. And perhaps we added one more thing, that if a carbon with the double bond has H on it, it converts itself into OH. For the sake of learning, let's have one more example. I'm making a more complicated structure over here. We will name this compound as the reactant, and then we'll also try to make the products with cold dilute and even hot concentrated manganate. Let's number this carbon structure with carbon number 1, 2, 3, 4, 5, and 6. There's a double bond between carbon number 1 and carbon number 2, the red yellow, and there's a double bond between carbon 4 and carbon 5. When we name it, we have numbered it already, right? So we'll call it in a way that the name becomes, it has no branch literally. When we name it, it becomes hex 1,4-diene. Instead of calling it hexene, we'll call it hexdiene. Now let's talk about the bonds and the structure with cold dilute acidified manganate. We keep the whole structure intact with the 6 carbons, but this time no carbon-carbon double bond. All the H's remain the same. Carbon 2 has H on top, carbon 3 has H on top at bottom, carbon 4 has H, carbon 5 has H, carbon 6 was CH3. To keep things simpler, let's number it 1, 2, 3, 4, 5, 6. The red, the yellow, the green, the blue. All these carbons get OHs. So 1, 2 get OHs, 4 and 5 get OHs. Now we have a tetraol, by the way. So it is a compound with 4 hydroxyl groups. Very much possible. We can have that, so it's nothing out of the blue. But remember, now when we talk about the structure with hot, concentrated, acidified manganate, you have 2 carbon-carbon double bonds. So here, these structures will split in a way that you will get 3 products. The first product is made from the red carbon. The second product is made from the green carbon. The third product is made from the center, which will involve the yellow and the blue carbon. You can see carbon number 1, the red carbon, has 2 H's. Remember, it's on the terminal. So we literally get carbon dioxide molecule out of this. Terminal carbons, it's the terminal carbon, by the way, it's the terminal carbon-carbon double bond. Terminal carbon-carbon double bond. We get carbon dioxide. Then the product from the green carbon. So the green carbon, which was carbon number 5 in our structure, has methyl. We will never change the methyl. Instead of the carbon-carbon double bond, we attach oxygen atom. And what about this H? Do we change the H? Yes, we do. What do we make? We make OH group. So we'll make OH group here. Now when you look at this structure, it's a carboxylic acid because it has the carboxylic acid functional group. So it's an acid. What about the last product? So now you can see carbon number. Let me remove the let me move the second product. Let me move it here. Yeah. Carbon number 2, carbon number 3, and carbon number 4. You can notice that carbon number 2 was the yellow one, carbon number 4 was the blue one. Carbon number 2 has H on top, so the H converts itself into the OH. If it's a direct H, they become OH. Carbon number 3 remains the same, so I'm not changing carbon 3, which was in the middle, because we don't care about it. It had no double-double bond, right? So we don't care about it. If you notice carbon number 4, it also has H. It will also become the OH. And what about their double bonds? The carbon-carbon double bond breaks down and they make bond with oxygen atoms. You can see if I number it, it was your carbon number 2 and carbon 3 and carbon 4. You can see the carbon 2, which was here, it has made a bond with OH and the oxygen, which is a carboxylic acid functional group. Carbon 3 literally remains the same, so we don't change it. Carbon number 3 literally remains the same. While the carbon 4 converts the H into OH, and instead of the double bond with the carbon, it gets a double bond with oxygen. If you notice this structure, it has 2 carboxylic acid functional group, one towards the left, one towards the right. So we will call it a dioic acid. Those are called dioic acids. It's a propane dioic acid because it's a 3 carbon 2 carboxylic acid compound. It has 3 carbons but 2 acids. So these are your 3 products. Product number 1, product number 2, and product number 3. So there are 3 products made. Let me put dotted lines around so we know that these are your different products. Yes, these are your 3 products. Number 1, which is a gas. Number 2, which is a carboxylic acid. Number 3, which is again a dioic acid. So in today's video, we revised the reaction of oxidation of alkenes, we said that the cold dilute acidified manganate, which is by the way purple in color, or the hot concentrated manganate, which is again purple in color, has two different kinds of reactions. We said that the cold dilute manganate will only break the pi bond, so it only breaks pi bond and attaches OH groups. The hot concentrated breaks sigma, pi, both bonds, so the carbon-carbon bond cleavage happens and you get normally two products. Why am I saying normally? Because we'll do some examples which are more trickier. We did some examples, we noticed few things. Number one, the terminal carbon-carbon double bond becomes carbon dioxide. We studied the second portion that if a carbon-carbon double bond has methyl group, it remains the same. But if it has H, the H will become OH. So we should consider these ideas while we are doing these questions. Stay tuned, guys. Thanks.